It's kind of amazing when you actually stop and think about it. How do we really figure out what someone knows or what they can do?
Right. We use tests, assessments, all these measurements all the time.
Exactly. But what are the actual, fundamental ideas behind them? How do they even work?
That's precisely what we're digging into today. We're doing a deep dive into the core concepts, assessment, measurement, and testing.
And we're drawing heavily on the work of Professor Jae Choi at George Washington University, specifically his lecture module, How to Conceive Assessment, Measurement, and Testing.
Yeah, it's a really thorough resource. He lays out the definitions, the history, the key concepts.
So our mission for you listening is to unpack all of that. We want to pull out the essentials, look at how these ideas developed, and give you a really solid grasp of the principles.
And hopefully do it in a way that's clear, engaging, avoids too much jargon.
Definitely. Because understanding this stuff is pretty crucial in a lot of areas. So where should we start? Maybe the
The
history.
history is actually fascinating. It
Mhm.
shows this isn't a new idea at all.
Right. Professor Choi mentions testing public officials in China way, way back, like 2200 BCE. Can you imagine?
Seriously, the pressure must have been immense. But jumping ahead quite a bit, we start seeing more formal thinking about measurement emerge.
Like Descartes.
Exactly. Descartes in 1644. His statement was basically, if something exists, it exists in some amount, and if it exists in an amount, well, it can be measured.
That's a pretty foundational thought, isn't it? Sort of opens the door to quantifying almost anything.
It really does. Then the 19th century, things really start cooking. You've got Francis Galton, 1869, working on correlation.
Which is huge for understanding how different things we measure might relate to each other.
Absolutely. And then in 1890, James Cadell actually coins the term mental test.
Okay, so the language is starting to solidify. We're starting to see a field forming.
Precisely. And the early 20th century is just packed with milestones. The college entrance examination board, the College Board gets set up in 1900.
A big one.
Huge. Then, 1905, Alfred Binet and Theodore Simon developed the first actual intelligence test.
Uh,
That was revolutionary, trying to put a number on cognitive ability.
And that test evolved, right, into the Stanford Binet?
Yeah, the Stanford Binet revision came in 1916. And alongside that, remember the College Board? In 1926, they introduced the SAT, the Scholastic Aptitude Test.
Which, wow, has certainly had a long history in education.
Definitely.
Sure.
And it wasn't just practical tests being developed. You had major theoretical advances, too. Spearman, 1927, with his theory of general and specific intelligence, G on L's factors.
Trying to understand the structure of intelligence itself.
Right. Then the late 30s, early 40s, a real burst of activity. The Mental Measurements Yearbook started publication in 38, still a vital resource today.
For finding info on tests.
Exactly. Then the Wechsler-Bellevue Intelligence Scale in 39, the MMPI Minnesota Multiphasic Personality Inventory in 1940.
So intelligence, personality, the scope is widening.
And Raymond Cattell adds his theory of fluid and crystallized intelligence in 1941.
Now, Professor Choi includes a fun factoid around this time.
Ah, yes. M&Ms were invented in 1941.
And apparently used in some classroom demonstrations. Seems random.
A little bit. But it's a quirky reminder of how things intersect. Anyway, moving into the post-World War II era, the focus broadens even more.
Okay, what happens then?
Well, 1942 sees the start of the GED General Education Development Testing. And a really big development in 47 was the creation of ETSPS, the Educational Testing Service.
PTS, yeah, they're a major player.
Huge. Then in 57, Donald Super's theory of career development starts bringing measurement into vocational guidance.
So testing is branching out beyond just academic settings.
Definitely. And the social and legal side starts becoming much more prominent. The Civil Rights Act in 64, the Coleman Report in 66.
Highlighting educational equity and how assessment plays into that.
Exactly. Then you get the National Assessment of Educational Progress, NAEP, starting in 1970, our nation's report card.
Gives us that national benchmark.
Right. And FERPA in 74, the Family Educational Rights and Privacy Act, emphasizing student data protection.
Very important.
Then the late 70s, you have Holland's work classifying careers in 75, the Education for All Handicapped Children Act, also in 75, truth in testing legislation in 79, pushing for transparency.
A lot happening towards the end of the 70s.
Yeah, and then jump to 2001, and you get the No Child Left Behind Act, which dramatically increased the role of standardized testing in U.S. schools.
Right, that had massive implications. So this whole timeline really shows an evolution from simple official selection to complex theories, widespread standardized tests, and legal frameworks.
It really does. It's shaped by scientific advances, social needs, legal requirements. It's a dynamic history.
Okay, that's a great backdrop. Let's pivot to the core definitions Professor Choi lays out. Starting with the absolute basics,
Good.
what exactly is a test?
It's defined really broadly in the module. A test is basically any tool, procedure, device, examination, investigation, essentially any way of measuring an outcome.
An outcome usually being some kind of behavior, right?
Typically, yes. Some kind of observable behavior or performance. The key is flexibility. A test isn't just pen and paper. It could be an observation, a simulation, an interview.
Gotcha. So how does measurement fit in? Is it different from a test?
Measurement is the process of quantifying attributes.
Yeah.
So you use a test to perform measurement. It's about assigning numbers to characteristics of an object or event, usually so we can make comparisons.
So taking something qualitative, like knowledge, and making it quantitative.
Exactly. Professor Choi also calls it a systematic process of assigning numbers to attributes. The system, the rules you use, that's key.
Okay. Now, another pair of terms that often get confused. Variable versus data. What's the distinction there?
Good question. A variable is the characteristic or attribute itself that can differ among individuals or objects. Think height, test score, anxiety level, these things vary.
Right.
Data are the actual specific values or pieces of information you collect about those variables. So if test score is your variable, the actual score is 85, 92, 71. That's your data.
So variable is the concept. Data is the specific instance or value.
Precisely. Technically, data are sets of values, and a single value is a datum. Professor Choi uses that elephant analogy, which is helpful.
Ah, right. The elephant. Explain that one.
Okay, so imagine the elephant is the thing you want to understand. Maybe size is the variable. You can't just grasp size directly.
Oh, right.
So you collect data, you measure its height, its weight, maybe its length. Those specific measurements, those are the data points that help you describe the variable, size.
Okay, that makes it much clearer. The abstract thing versus the concrete numbers we collect. Great. So why do we do all this? Why assess, test, or measure? What are the main purposes?
Professor Choi lists several key purposes. One is selection.
Like choosing applicants for a job or a university?
Exactly. Using tests to pick people who meet certain criteria. Another is placement.
Putting students in the right level of a course, maybe?
Yes, or assigning someone to the right training program based on their current skills. Then there's diagnosis.
Figuring out specific strengths or weaknesses, like a learning disability or where someone needs help.
Precisely. Identifying specific needs or problems. There's also hypothesis testing.
Ah, for research. Using measurements to see if a theory holds up.
Right. Gathering evidence. And finally, classification.
Grouping things based on shared features, like types of personality.
Exactly. Categorizing based on assessment results.
Mm-hmm.
And, as you're listening, it's useful to think where you've seen these purposes play out in your own experience.
Good point. Makes it less abstract.
Yeah.
Okay, so that's the why. What about the what? What kinds of things do we typically try to measure?
The module highlights some common domains. Achievement is a big one, measuring what someone has learned, say, in history class.
Makes sense. What else?
Personality, looking at those stable traits, attitudes, characteristics. Think Myers-Briggs or the Big Five.
Okay.
Then aptitude. So this is more about potential predicting future success in a certain area, like mechanical aptitude.
So achievement is past learning.
Mhm.
Aptitude is future potential.
Roughly, yes, though the line can sometimes blur. Then there's ability or intelligence, measuring current cognitive skills or competence. IQ tests fall here.
Right.
And finally, vocation or career assessments, measuring interests related to jobs, helping people find suitable career paths.
It's quite a range of human attributes we try to quantify.
It is. And this connects to the idea of scalability. How do we take these abstract things and put them on a scale?
Yeah, what's the thinking behind that?
The underlying hypothesis is that the thing we're interested in, like extroversion or math ability, exists in varying amounts. People have more or less of it.
Okay.
And we believe we can create a scaling rule, a systematic way to assign numbers that represent those amounts on a theoretical line, a unidimensional continuum from low to high.
Like a ruler for psychological traits.
Sort of, yeah.
Yeah.
And ideally, we want the numbers on that scale to have certain properties.
Like what?
Like order a higher number means more of the trait. Like distance, the difference between a 2 and a 3 means the same amount of difference as between a 4 and a 5. And ideally, a meaningful origin or 0 point.
A true zero, meaning none of the trait. That sounds trickier for things like personality.
It is. That's one of the big challenges in psychometrics compared to, say, measuring length. Achieving all those ideal properties is tough.
Okay. Let's talk about the actual scores we get. We hear about test scores, item scores. How do they relate?
Right. So an item score is the score on a single question or task within a test. Maybe 1 point for correct, 0 for incorrect.
Simple enough.
Then, very often, the test score, or total score, or summed score, or composite score, these terms are often used interchangeably, is created by adding up those individual item scores.
So your total score reflects your performance across all the items.
Exactly. It's a way of aggregating the information from multiple specific behaviors, responses to items, to get an overall picture of the construct.
Okay. But often, these raw total scores aren't what get reported, right? We hear about scale scores. Why do we convert them?
That's a great point. Raw scores like getting 40 out of 60 can be hard to interpret on their own. Is 40 good? Depends on the test difficulty, who else took it.
Right, needs context.
Exactly. So scale scores are transformations of those raw scores, or sometimes scores from more complex models like IRT, onto a new scale with defined properties.
What's the benefit?
The main goal is easier interpretation. Scale scores often have a standard, meaning maybe an average is set to 100 or 500. This helps you immediately see how a score compares to a reference group. It increases comparability across different test forms or versions, too.
So it standardizes things and makes them more meaningful?
Precisely. It helps reduce confusion and allows for better comparisons. Scale scores are also used to set CUD scores.
Like pass-fail marks? Or different proficiency levels?
Yes, exactly. Defining those important thresholds on the measurement scale. The official standards for testing emphasize this conversion to scale scores to help users understand the results.
Professor Choi provides a table example showing item and test scores, doesn't he? Can we walk through that quickly?
Sure. It's a simple example, but illustrates the point. You see, say, 10 examinees and their scores on 5 items, maybe zeros and ones.
Oh,
For each examinee, their total score is just the sum of their scores on those 5 items. Examinee A gets 0, 1, 0, 1, 0, total score is 2. Examinee B gets different scores, maybe a total of 4.
and the table also shows averages.
Yeah, it just shows the average score on each item across all the examinees, which tells you about item difficulty and the average total score for the whole group. Just shows that basic aggregation process.
Got it. Simple summing up. But the way we think about how those scores relate to the underlying thing we're measuring, that involves measurement models, right? Professor Choi discusses a few.
Yes, different ways to conceptualize the relationship between the construct and the scores. One is the emergent measurement model or composite score model.
How does that one work?
The idea here is that the construct kind of emerges from the sum of the parts. You add up the item responses to get an observed score, and that observed score is taken as your estimate of the true underlying ability or trait, plus some error.
So the items cause the score, in a way?
You can think of it like that, yes. The total score is built up from the components.
Okay, what's the alternative? The latent measurement model.
Right. In latent variable models, the direction's reversed. We assume there's an unobservable latent trait, like mathematical reasoning ability, that causes the person's responses on the test items.
Ah, so the underlying trait influences the observable scores.
Exactly. One version uses parallel assessments. The latent trait influences performance on several similar tests, and by looking across them, we estimate the latent score.
And the other version?
The other involves observable components or parts. The latent trait influences different specific aspects or components or performance, each measured with some error. Again, the underlying trait is seen as the cause of the observed performances.
So emergent is bottom-up, latent is top-down, conceptually.
That's a decent way to think about the difference in perspective. Professor Choi also briefly mentions more complex psychometric models, ISA, part of, sequential, hierarchical.
Those sound complicated.
They represent more intricate ways to model the structure, suggesting relationships beyond simple summing or direct influence, like hierarchies or sequences. It acknowledges that the connection between a trait and how it shows up can be quite complex.
Okay. Shifting gears slightly, let's talk about the measurement approach. Subject-centered versus stimulus-centered. What's the difference there?
The main difference is the focus. In subject-centered measurement, the main interest is in the people taking the test. We want to differentiate between individuals who has more or less of the trait. We want to place them on the scale.
So the test items are tools to measure the subjects.
Right. In stimulus-centered approaches, the focus flips. The interest is in the test items or stimuli themselves. The goal is to place the stimuli on a scale. For example, determining the difficulty level of each test question based on how people respond, or maybe the intensity of different attitude statements. We're using the people's responses to measure the items.
That's a neat distinction. Measuring the person versus measuring the item. Okay, let's think about measurement in different domains. Professor Choi touches on the physical domain and the metric system.
Yeah, it's a useful comparison. In the physical world, many of our measurement units started from basically historical agreements or conveniences.
Like the length of a king's foot.
Maybe not quite that arbitrary anymore, but standards evolved over time. Communities needed common benchmarks, especially for trade, leading to laws against fraud. Now, some are tied to fundamental physical constants, which is very precise.
And the metric system brought a lot of order to that.
Absolutely. A decimal-based system built on units like the meter and kilogram has gone through refinements leading to the SI, International System of Units we use globally now. It's designed for consistency, ease of use, especially in science.
Makes sense. What about in economics? How does the unit of account function as a measurement tool?
Money, in its role as a unit of account, provides a standard measure of economic value. It lets us compare the costs of different goods, track profits, assess the financial health of a company.
So it allows for meaningful comparisons and calculations.
Yes, it's crucial for economic decision-making and efficiency in markets. Shareholders need it to understand performance.
But it's not perfectly stable, is it?
That's the catch. Unlike a kilogram, the value of a dollar or euro changes over time because of inflation or deflation.
Right. So inflation messes with the stability of that unit of measure.
Exactly. It undermines the assumption of a constant value, which is a challenge for things like long-term accounting.
A good reminder that even seemingly precise measures can have complexities. Now, Professor Choi uses a diagram to show a psychophysical spectrum of human attributes. What's that about?
It's a way to visualize that human traits exist on a continuum. At one end, you have purely psychological latent traits that aren't directly observable, things like attitudes or intelligence.
Okay.
At the other end, you have directly observable physical traits, height, weight, reaction time. And there's overlap in the middle. Some traits might have both psychological and physical aspects.
So it acknowledges the range from internal states to external characteristics. And then, focusing specifically on the psychological side, there's the metric spectrum of the psychometric domain.
Right. This looks at the types of scales we can potentially use to measure those psychological or latent traits like personality, attitudes, knowledge.
What are the different scale types mentioned?
He shows how different domains might map onto different scales.
Yeah.
Some might only be measurable on a nominal scale, just categories, like classifying personality types without ordering them.
Just labels.
Exactly. Others might allow for ordinal scales where there's a clear order, more or less, of the trait, or even interval scales where the distance between points is meaningful, like maybe on some attitude scales, but often without a true zero.
Right. Zero attitude doesn't mean much.
Exactly. And then for things like knowledge or cognitive ability, we might sometimes aim for or approximate a ratio scale, which does have a meaningful 0.00 correct answers, could mean zero knowledge on that specific test.
So the type of trait influences the type of measurement scale we can realistically use.
That's a key takeaway. Now, let's make this even more concrete. Professor Choi includes a table summarizing the main types of tests. Can you give us an overview?
Sure, it's a helpful breakdown.
First, achievement tests. These measure what you've learned in a specific area. Think end-of-unit exams, professional certification tests. Examples given are things like the closed high school placement test or early school assessment.
Okay, measuring acquired knowledge.
Then personality tests.
Yeah.
These assess those unique, stable traits, characteristics, attitudes. Examples include the achievement motivation profile or the aggression questionnaire.
Measuring who you are, in a sense.
Kind of. Then aptitude tests. These aim to predict your potential to succeed in the future. Things like the differential aptitude tests or the scholastic aptitude scale.
Looking ahead.
Exactly. Then ability or intelligence tests, measuring current skill or competence. Famous examples are the Wechsler scales, like WISC, or the Stanford-Binet.
Assessing cognitive horsepower.
You could say that. Performance tests measure how well you can actually do particular tasks. Might involve observation or simulation. Examples: Achenbach's system of empirically based assessment in nursery education.
More hands-on assessment.
Often, yes. And finally, vocational or career tests, measuring job-related interest to help with career choices. Examples: Adaptive Functioning Index, Career Interest Inventory.
Quite a variety. And the Burroughs Center for Testing is mentioned as a resource.
Yes, a great place to find detailed reviews and information about thousands of commercially available tests.
Good to know. Okay, as we wrap up this exploration of the core concepts, Professor Choi offers some important reminders and constraints. What are the key things we absolutely need to keep in mind?
Several crucial points. First, some behaviors are just inherently easier to observe and measure accurately than others. Measuring typing speed is more straightforward than measuring creativity.
Sure.
Second, our understanding is always limited by the quality of our tools. A bad test gives bad information, no matter how sophisticated our analysis is.
Garbage in, garbage out.
Pretty much. Also, tests aren't just one thing, they come in many forms. And crucially, test results must be interpreted in context. Where, when, why, and how was the test given?
Context matters hugely. Like the shift to digital assessment, that changes the context too.
Absolutely. And maybe the most critical point, test results can be misused. We need to be ethical and careful.
That's a huge responsibility. He also notes many achievement tests aim to differentiate between those who know the material and those who don't.
Right, that's often a primary goal, making distinctions based on acquired knowledge.
These are vital caveats. Finally, the module lists some ATM concepts for further exploration. Looks like a good list for anyone wanting to go deeper.
Definitely. It includes fundamental distinctions like reliability versus validity, hugely important. Measurement itself, quantification, operationalization, the difference between latent traits and observables, discrete versus continuous traits, knowledge versus intelligence, and fluid versus crystallized intelligence.
Lots of core psychometric ideas there.
And also different assessment approaches, summative versus formative assessment, analog versus digital, and adaptive or tailored testing versus non-adaptive. It really maps out the territory for further learning.
And for those really interested, Professor Choi mentions his Toy Friend videos on statistics and this very topic: assessment, measurement, and testing. English versions on YouTube, Korean versions pending.
Great resources to check out.
So, learner, we've covered a lot of ground today working through Professor Choi's framework for understanding assessment, measurement, and testing.
We hope breaking down the history, the definitions, the models, and the types of tests has given you a clearer picture of this really important field.
Yeah, getting a handle on these fundamentals really does equip you to better understand and evaluate the assessments you encounter everywhere, in education, work, even daily life.
Absolutely. And maybe a final thought to leave you with. Reflect on how this historical journey of testing has shaped our current world, especially in schools and workplaces.
And maybe question the assumptions behind the different measurements we see every day. What are we really measuring, and how good are the tools we're using?
Thinking critically about these tools is key. It's not just about the numbers. It's about understanding what they represent and what they don't.